Hello, my name is Tilson Galloway, and this video will highlight some of our work related to practical attacks against DNS reputation systems. This is work done at Georgia Tech alongside some great folks from Oregon State University and the University of Georgia. So what are DNS reputation systems? These are systems that flag domains as malicious using a combination of statistical features, machine learning, and heuristic methods. They use information about the attributes of a domain, like its lexical features, its relationships to other IP addresses, domain names, and networks, as well as lookup behaviors, all in service of providing early detection of malicious domains. The information that are used for this feature extraction is sourced from a diverse set of data sets. The domain names themselves come from recursive authoritative DNS data sets, as well as active lookups to domains, as well as certificate transparency logs. This data is then enriched with whois information to grab registration lengths and ages, BGP routes to gather information about IP addresses network, and IP block lists to see some of the historical evidence associated with an IP address. The outputs of these systems are incorporated by many entities across industry. We see email services who use these systems to reject emails from low reputation domains, also to block phishing lures that are included in the email content. We also see firewalls and web browsers use these systems to protect their users against bad domain names. Finally, we see these used in registrars. These registrars use DNS reputation systems to suspend malicious domains early before they can be used maliciously. So the two research questions that we ask in our work are: how can an adversary evade these ML-based systems? We find that they can. The second question is, we find these attacks that are effective against academic models, but do these tactics work in the real world, and how practical are they? We ultimately find that for the cost of $10 and 14 days of effort, an adversary can evade both academic and industry models. So our work is divided into two major parts. There's the building of the reference model, and then there's the evasion. Our reference model was built using prior academic work and active DNS data. This academic work is based on top-tier security conferences from the last 10 years, and the active DNS data is a freely available data set provided by Georgia Tech. From this, we implemented 50-plus statistical features that cover 9 different feature groups. To ensure that our work is reproducible, we open-sourced implementations of these feature extraction. This reference model allows us to rapidly emulate and evaluate our evasion techniques locally and in a sandbox and secure environment. This is different than a lot of other ML settings. In a lot of other ML settings, there are gradient techniques that are used to manipulate features in the feature space, although here we do our attacks in the problem space. This is because the problem space is highly contained. Adding a DNS record can greatly change your feature in a very unexpected way. Additionally, the feature space is non-invertible. You might have 2 domains that map to the same feature vector entirely. These tactics are ultimately informing attack plans. Then we test these attack plans against a real-world security vendor. We also address the practicality of these attacks. We judge each of our attacks based on the financial cost and the time it took to carry out the attack. Although we use a variety of features in our reference model, the basic unit in this reputation system is the resource record. We specifically look at type A and quad A resource records that map a domain name, here IEEE.org, to an IP address. Some features can be extracted directly from the domain name. For example, lexical features like the entropy or the length of the domain don't require any additional sources. Other features do require additional sources. For example, we use whois data to grab the registration length and age of the domain. Generally, a longer registration length and age is associated with benignness. We're also interested in the network infrastructure and the related domains when we're classifying a particular domain. To do this, we use historical DNS data as well as current DNS resolutions to find features that are associated with the domain's IP address and its historic IP addresses, as well as its autonomous systems and BGP prefixes. We also use these networks to pivot on the domain and find features of the other domains that share that IP address. Finally, we enrich our domains with information from 2 more places: popularity lists and IP block lists. The popularity lists give us an idea of the amount of traffic that is destined to a domain name through its popularity ranking. And the IP block lists give us information about the reputation of a particular IP address or a network. Is the network contain a lot of malicious traffic? That's what the IP block lists tell us. Although we have a lot of features, we find that there's 3 feature groups that really contain the majority of the information needed for classification. Therefore, we focus on historic records and popularity lists for our evasion attacks. Let's start by talking about mimicry attacks. These attacks look at features that are based on historic IP relationships, and they have no additional financial cost nor a significant time investment. Here's an example of how it works. These 2 malicious domains are connected using a malicious IP address. The 2 benign domains are using a separate IP address, so the malicious domains and the benign domains have no connection to each other. The malicious domains are, of course, related by this one IP address. The mimicry attack comes into play when the malicious domain becomes pointed at one of the benign IP addresses, which alters the feature distribution for the malicious domain. We find that just by doing this, you can increase the reputation of your domain by 25 points. And when you combine it with other attacks, it is enough to evade the model entirely. This comes at a cost, however, of introducing a small resolution error when it is active. This can usually be mitigated by using the historical references. Most of these reputation systems use historical records, and so you can prime the model with these historic records that you're doing the mimicry attack, and then once the actual campaign starts, you can stop performing the mimicry attack. Even when current IP addresses are used, however, a C2 communication can mitigate this using custom resolution software. The second attack we consider in this video is the popularity list attack. These are motivated by the fact that many systems use popularity lists as their ground truth, either directly in the benign training and evaluation and test sets, or sometimes we've seen hard allow listing in real-world systems for this. These popularity lists are often based on open DNS recursive resolvers, meaning that anybody can make DNS lookups to these resolvers. Therefore, we can manipulate these lists. The way we do this is we have a $10 VPN subscription that sends 1 DNS query per IP address to the resolver. We then disconnect from the VPN, reconnect to the VPN, and receive a new IP address. We found that this technique gives us over 12,000 unique IP addresses every day, which allows us to achieve a rank of 250,000 on Cisco Umbrella and Cloudflare Radar. The Trenko list, which is a often used popularity list in both academia and in industry, averages popularity from these multiple different sources over time. This blue curve on the right shows that we can manipulate this to 1 million in 10 days and to 500,000 in 14 days. So we've shown that these attacks are practical when it comes to financial cost and time, and we've shown that they're effective against academic models. But do they work against real-world models and systems? These real-world systems don't just use machine learning, they use pre-processing and filtering and all sorts of other methods that are a black box to an attacker. So to answer this question, we partnered with an anonymous security vendor, and we submitted 8 malicious binaries to this vendor. The reason that we did 8 malicious binaries rather than uploading the domains by themselves is because we found the default state of a domain is benign. Therefore, we needed something to put ourselves at a disadvantage. In this case, it's having these malicious binaries resolve the domain names. We ultimately found that a popularity ranking of 500,000 along with mimicry leads to evasion. This costs $10 in 14 days, and a 2-year registration length in addition to memory similarly results in evasion. This costs a little more, and this cost is also per domain, as you have to register each domain for 2 years. Although it's easy to evade these systems from real-world vendors, it's important to put it in perspective. It's not because these vendors are negligent or charlatans. It's more because these vendors are incredibly false positive avoidant. A list missing a couple of malicious domains is not as bad as a list resulting in a domain suspension or denial of service for a set of benign domains. In addition to these 2 attacks against the reputation system itself, we also found 2 sandbox-specific attacks that were effective against the security vendor. First, we found that if a domain name appears in the strings of a binary, but dynamic analysis does not cover the actual lookup of the domain is identified, but it still is evading the model. We similarly found that using an encrypted DNS protocol results in evasion because there's no memory inspection coming from the sandbox. So to sum it up, we found that DNS reputation systems are not robust to evasion attacks. It only costs $10 in 2 weeks of effort or $15 in under a day to evade popular security vendors and academic models. As a result, we think that operators should consider more thoroughly the trade-off between key features and a model's performance and the susceptibility of those features to evasion.